Right, so I'm going to start by sort of introducing variational quantum algorithms, and then I'm going to try and pin down requirements for a variational quantum algorithm to be effective. I'm going to focus in on two in particular, and these are the expressibility of the ansatz, as well as the trainability of the ansatz and cost function. So I'm going to spend quite a while trying to sort of pin down exactly what I mean by these terms, both heuristically and a bit more concretely, before presenting some prior results on them. And then I'm going to hone in on some of my own results on these two requirements. So the first of these is a trade-off between them. So a bound showing that you cannot have both. You cannot have an ansatz that's both expressible and trainable. And then the second, so that's the result in this first paper here, connecting ansatz expressibility to gradient magnitudes and barren plateaus. And then the second thing I'm going to talk about is a sort of fundamental limit on variational quantum algorithms, quantum machine learning, saying that not all ansatz are trainable. You can't apply variational quantum algorithms to all target problems because there can be a trainability roadblock. Specifically, you cannot use variational quantum algorithms or quantum machine learning algorithms more generally to learn scrambling or more generally random unit trees. Okay, so that's the overview. But let me start by going back 10 steps and giving you my take on variational quantum algorithms. Now, I appreciate many of you will be very familiar with this already, but it's always good to repeat things, and maybe some of you aren't so familiar with this. So variational quantum algorithms are good candidate algorithms for near-term quantum computers. So near-term quantum computers are the kind of things that Google are building at the moment. They're incredibly impressive pieces of engineering, but if we're honest with ourselves from a user's perspective, they can be quite hard to use. So Elisa, for example, knows this very well. They are rather noisy, and they're certainly far too noisy to run error correction. And so we need to find ways of working with them despite their noise levels and, of course, small size. So variational quantum algorithms are good candidate algorithms for near-term quantum computers because they only run a classically hard subcomponent of the algorithm on the quantum computer and then offload the rest of the algorithm onto the classical computer. And this is clearly less demanding on the quantum computer. Typically, they are optimization algorithms solving an optimization problem, but with your cost function evaluated on the quantum computer and the optimization done classically. So let me go into a little bit more detail about how these work. So the idea is you are going to run some parameterized quantum circuit on your quantum computer for a particular set of parameters. You will then perform some measurement, and that will give you your cost function for a particular choice in parameters. This is fed to your classical computer. The classical computer runs its favorite optimization algorithm to tell the quantum computer what parameters to try next. The quantum computer runs a new circuit with a new set of parameters, it spits out a new cost for the new parameters, and you keep on looping around until you've minimized your cost. And the parameters that minimize your cost, or the unitary with respect to those parameters, or the state prepared by the unitary with respect to those parameters, will in some sense be a solution to your optimization problem. But this can be made more concrete by considering examples. So the classic example is, and sort of the first example of a variational quantum algorithm is a variational quantum Eigensolver. This was presented by Barroso and McLean et al. Back in 2014. So the idea here is that you will take your cost function to just be the energy of a particular Hamiltonian. And so by minimizing the energy of this Hamiltonian, so the average energy of this Hamiltonian with respect to a particular state you prepare, you can find the ground state energy and the ground state of that Hamiltonian. So what you do is you prepare a test state, some psi of theta, by applying some unitary u of theta, and then you measure the energy of that state psi of theta with respect to the Hamiltonian you're interested in finding the ground state of. And this is typically done by expanding your Hamiltonian as a sum of Pauli's, and then just doing a bunch of Pauli measurements here. So you can see that by looping around and minimizing this cost, you will find the state that minimizes the energy of the Hamiltonian, which is precisely the ground state, and its associated energy is just going to be ground state energy. So this is useful for a whole host of things, such as quantum chemistry and condensed matter problems, but also, as I will sort of hopefully become clear as this talk goes on, many other problems can be encoded into a cost function of this form. Okay, so my second example is you can use variational quantum algorithms to try and learn a target unitary. So that is, learn its form or find an optimized quantum circuit that agrees with the target unitary. Okay, so how would you go about doing this? Well, the idea would be to pick a cost function such that the unitary that minimizes your cost function matches your target unitary. So general form of a compiling cost, a cost to try and learn a target unitary, will typically be of roughly this form. So the idea is you prepare some initial state psi I, you let it evolve onto your target unitary, you then apply the inverse of your parameterized quantum circuit, and then you perform some measurement HI, and you repeat this averaging over different choices of initial state psi I and measurements HI. And the idea will be to try and pick your measurement HI such that the unitary that minimizes this cost matches your target unitary. Now, there are a number of different choices you could have for your HI here, but a really natural choice will be to just take your measurement operator to be a projector back onto the state psi I. In that case, this cost function here just measures the average gate fidelity. So that is the fidelity between a state psi I acted on by V and a state psi I acted on by your parameterized quantum circuit U theta, averaged over your different initial states psi I. Note that your state psi I here in the language of quantum machine learning will be considered your training data, your training states, the states that you know the action of your target unitary on. Okay, but that's the general idea. But that's sort of an example of a compiling cost, but more generally, the idea is to pick your cost such that the unitary that minimizes it matches your target unitary. Okay, so those are two examples, but there are many, many more examples of variational quantum algorithms that are out there in the literature. So this is one for not just finding the ground states of a particular Hamiltonian, but finding the excited states. This is another one along those lines. You find the excited states and then you use that to form a quantum simulation. This, more familiar names again, is for diagonalizing a quantum state. This one for sort of compressing quantum data from a larger system onto a smaller system so it can be stored more easily. This is one for solving linear systems equations, one for solving nonlinear problems, another one for linear systems equations. Those two came out at a similar time. This is one for preparing thermal states. This is one for even sort of probing the foundations of quantum mechanics by finding variational consistent histories, which is a sort of way of studying decoherence in quantum regimes. Okay, so there are a lot of variational quantum algorithms out there. That is honestly a tiny, tiny snapshot. But the field is often criticized for being a little too heuristic. And certainly it would be desirable to have some sort of more analytic results to guide their development and quantify their expected performance. This should help us develop new algorithms and also successfully implement the ones already out there. And it's really against that backdrop that the rest of this talk sits. Okay, so firstly, let me just take a step back and again pin down sort of the framework I'm considering here. So for the purpose of this talk, I'm going to consider cost functions of this form. So you just have some initial state, you evolve it under parameterized quantum circuit, and then you measure some measurement operator. So the VQE cost is of this form, but also a large class of problems can be solved using cost functions or broadly this form. And also in the papers that this talk is based on, we do consider some slightly more general costs. But for the purpose of this talk, I'm going to keep it simple and just talk about a cost of this form. Okay, so having decided you're going to have a cost function and you've got a target problem, the first thing you need to do is to pick your cost functions that is fatal. That is, you need it to be the case such that your cost is equal to 0 for a particular set of parameters, if and only if the unitary corresponding to those parameters is in the set of approximate solutions to your problem. So by set of approximate solutions, I mean, so for trying to learn a target unitary, it's just going to be your target unitary itself and unitaries that well approximate it. For trying to find a ground state, it will be the unitary that prepares your ground state as well as, or the unitary that prepares the ground states, plural, if it's a degenerate ground state space, as well as states that, or unitaries that well approximate those unitaries. Okay, the first thing you need is that your corresponding is faithful. The second thing you need to do is you need to pick an ansatz for your parameterized quantum circuit. So that is, you need to decide where you're going to put your gates and what rotation angles you're going to parameterize. So you can have discrete parameterizations, but typically you will have continuous parameterizations where your parameters are just rotation angles of various gates. And a very wide class of ansatz can be written in this form. So that is, you're going to have alternating layers of fixed gates and parameterized rotations. So your fixed gates can be anything really. In this diagram on the right here, they're just ladders of ZZ gates. And your parameterized rotations, well, I'm going to assume that they're of this form. So just e to the minus I theta Vj, where Vj is Hermitian. And it's helpful to assume that your Vj's also square to the identity. So your Vj's could be single qubit Pauli operators or multi-qubit Pauli operators, or anything that really satisfies these conditions. So on the diagram I've got to the left here, they are just simply single qubit rotations, but it could be much more general than that.
So Zoe,
Yes.
Soria had a question in the chat. Is there a specific reason for 0 to be the faithful condition?
No, not at all. You just need it to be the minima, strictly actually. So you just need that the cost function is minimized if and only if the solution so what you need, it was simple to state this for the purpose of the talk, but you're completely right, it doesn't need to be 0. What you want is that the theta that minimizes your cost, the unitary corresponding to the theta that minimizes your cost is contained within the approximate set of solutions. And also the theta that minimizes your cost, that the theta, any theta that is in your set of solutions minimize your cost. So it doesn't need to be 0, it just needs to be the minima.
Thank you.
Cool. So what I was going to say is this ansatz structure is very general. So note that the WJs can change between layers. They could be sort of highly non-local gates, ditto for the parameterized rotations. The only constraint that I'm going to put on is that I'm going to assume for now, at least, that the parameters are uncorrelated. Okay. So once you've fixed your ansatz structure, then given any set of possible input parameters, so bold theta here is a vector of theta 1, theta 2, theta 3, all the way to theta 12. So corresponding to a set of input parameters, there's going to be a corresponding output unitary. And so corresponding to the set of all possible different input parameters that you're sort of under consideration, there will be a set of accessible unitaries. And for a variational quantum algorithm, what we need is that a solution unitary will be contained within that set of accessible unitaries. So we need the solution unitary to be captured by the ansatz. So we need this set of approximate solutions, the intersection of the set of approximate solutions and the set of accessible unitaries to be non-empty. So when this condition is satisfied, the ansatz is said to be complete. I think this is best understood pictorially. So here, the big gray oval is sort of the total space of unitaries. And this blue oval could be the set of unitaries accessible by your chosen ansatz. And then suppose there are two problems you're trying to solve, problem B and problem A. So they could be corresponding to two different target unitaries you're interested in learning. Well, the intersection between the set of accessible unitaries and the set of solution unitaries for problem A is non-empty. So this ansatz could be used to try and solve problem A, but you're not going to be able to use it to solve problem B because none of the solutions are contained within the ansatz. Okay. Now, in the absence of prior knowledge about where your solution lies, or if you want to come up with an ansatz that's going to work for a wide class of problems, your best bet is going to be to use an ansatz that explores the space of unitaries as fully and as uniformly as possible. So such ansatz are known as expressive ansatz. So
I have a question. Sorry, it's just a minor thing regarding terminology on the previous slide. Shouldn't you say complete for problem A?
Yes, I mean, so I guess I was following on from this line above. So up on this line, I didn't define what was a set of solutions for.
Okay, but it's understood like there's a solution set for a particular problem.
Correct. Yes, it's only ever relative to a particular problem.
Okay, thank you.
So yeah, the ansatz I showed on the previous slide Well, it doesn't explore the total space of unit trees very well. It's a small, narrow oval with lots of space that it's not exploring. And so it's hardly surprising that it only contains a solution to A and not B. And this is an inexpressive ansatz. In contrast, on the right here, we have an expressive ansatz, the one that explores the space of unit trees really well. And accordingly, it contains solutions to both A and B. So it's complete with respect to both A and B. You could use it potentially to solve both problems A and B. Okay, so that's sort of a pictorial understanding of expressibility. I'm now going to try and quantify it, pin it down a little bit more. And in essence, the expressibility of an ansatz can be quantified by comparing the ensemble of unit trees accessible by an ansatz to the maximally expressive uniform, i.e. Haar distribution of unit trees. And one way we do this is by introducing the expressibility operator A. So this is just the difference between the t-fold channel induced by a Haar random unit tree versus the t-fold channel induced by the ensemble of unit trees accessible by ansatz. And because this terminology is going to come up later, I'm just going to introduce now the idea of t-design. So an ensemble of unit trees form a t-design if the expressibility superoperator acting on some operator x equals 0 for any operator x. So that's what it is mathematically. More loosely, a t-design is an ensemble that looks random when considering functions of only at most t copies of u. So for example, the average of the cost I showed you earlier over an ensemble of unit trees that form one design is going to be equivalent to an average over the random distribution. And that's because we're just averaging over one copy of u and one copy of u dagger. And so if it forms a one design, well, it agrees with the Haar random distribution if you're only considering functions containing only one copy of u, and so it agrees. But if you were to try and look at, say, the average cost squared, and so the variance of cost over an ensemble of unit trees that form a one design, well, this is not going to be equivalent to a random distribution because now we're dealing with integrating a function involving two copies of u. But if we were to consider the average cost squared over an ensemble of unit trees that form a two design, then it is going to agree with the Haar distribution. Okay, so that's just the concept of a t-design because it's going to come up later. I introduced this definition in terms of a generic t, but in many cases it suffices only to consider up to second order. And for this talk, that's certainly the case. So I'm going to drop the subscript t, replace it with a 2, and now I just have this generic superoperator defined for the twofold case. And so now if a of x equals 0 for all x, then it means that the ensemble of unit trees u forms a two design. Okay. So we are interested in minimizing the cost of this form. So what we want to do is try and define expressibility dependent measures relative to our particular cost function. And these are the natural measures that we introduce. So these are sort of cost function dependent measures of expressibility. We have epsilon rho, which is just the expressibility superoperator acting on two copies of our initial state. So rho here is just psi sign, assuming that our input's pure. Our input could be a mixed state, in which case it would be rho, as measured by the 2 norm, but we actually in the paper consider some other norms. And then we have the Hamiltonian dependent expressibility measure epsilon h, which is just the expressibility superoperator acting on two copies of the measurement operator h. So if these measures are small, that means that the ensemble of unit trees accessible by the ansatz well replicates the Haar random distribution of unit trees. So that is, it well explores the total space of unit trees. So our ansatz is highly expressive. If these measures are large, then there's a big difference between the ensemble of unit trees accessible by the ansatz and the Haar distribution. So our ansatz is very inexpressive. Okay, so that's the definition of expressibility. And we want our ansatz to be expressible to maximize the probability that it contains a solution to the problem we're interested in. Okay, but just because your ansatz contains a solution doesn't mean you're actually going to be able to find it. It's like an Easter egg hunt. just because you're looking in the right room doesn't mean you'll actually find any X. Notice another question in the chat. Is it good to address it now? Because I'm about to move on to something else, or I can leave it to the end.
There's no questions in the chat.
Oh, okay, fine. I'll just add an icon 2 popping up. Cool.
I guess I have two, since you asked, there are two things that came to my mind. Like you could define measures in different ways, right? You made a particular choice. One thing is you could use one norm, and we've discussed a bit about that kind of thing. If you use the one norm, then this error would have, I think, a better operational meaning.
So I'm trying to remember what exactly we did in the paper. One thing we did was we also, so these are, I'm trying to remember whether, I will address the question, I'll have a look at the end about whether, I'll have a think about whether we definitely looked into using the one norm, and I can't remember how that worked out. I'll say one thing that I do remember worked out was, so we've got these sort of cost function dependent measures for expressibility. We also thought it'd be nice to formulate our results independently of the cost. So you've got expressibility measures that basically work for any cost that just depend on the ansatz. And so we reformulated our results in terms of the diamond norm in that case.
Okay.
But we get some awkward factors of dimension appearing. I don't think it ruined the bounds completely, but these ended up being the tightest bounds, as you'd expect, that when you actually use as much information as possible, you get the tightest bounds.
Yeah. The other thing that came to my mind is, rather than looking at an average, you could do a maximization over all V and W and look at the maximal possible difference. I don't know if that would be interesting or whether you considered that. You follow what I'm saying? Like the maximal difference between the sets. Maybe that wouldn't be as interesting a measure.
Do you mean the maximal difference between elements of the sets?
So like, forget the average over V, forget the average over U, and just look at a fixed V and a fixed U and their difference with respect to some norm. And then you could maximize that difference.
I don't think that would be as interesting.
Mm-hmm.
Because I don't think that would capture as well sort of the difference in these set sizes. Well, not set sizes, sort of what you care about is the total ensemble.
Mm-hmm. So
that would be something like the furthest distance between a point in there and a point in there.
Yeah.
So it might tell you that that distance is really big, but you could have that then joining up really well. It wouldn't draw a distinction between a whole different bunch of ansatz, so that you'd have a bunch of different ansatz.
So let me revise my suggestion. You pick a V and then you minimize over U, right? And then you do a maximization over V. Does this make sense? So like you would say for a fixed V, you want to know if there's a U. I don't know. Anyway, let me not derail your seminar.
Yeah. Also, yeah, I think the point still stands for those examples, that you'll capture maximum difference, but you won't really capture the difference in the areas as well.
Mm-hmm. Okay. Thank you.
Cool. So Easter egg hunt, just because you're looking in the right room doesn't mean you're going to find the X. Just because your ansatz contains a solution doesn't mean you'll actually be able to find the solution. So in the context of minimizing a cost, your cost landscape is going to need to be sufficiently featured to enable training. So I'm now going to talk about gradient descent, but much of what I say equally applies to other optimization methods. And a good way to picture gradient descent, for those of you who aren't aware of it, is to imagine that you are lost up a mountain in the fog, as is quite common in the UK, but idiotically don't have a map or any idea where you are. Well, a decent bet as to how to get down would be to just keep on following the steepest route down at any moment in time, which is roughly what water does, which is why this red stick figure man is going to end up following the stream back down to safety. But this is only going to work if you can actually figure out which is the steepest route down at any moment in time. It's not going to work if the landscape is almost entirely flat. So imagine trying to find the lowest point on this field on the right. It's not going to work. Two directions are going to feel equally steep unless you can have very, very precise measurements. And so you're going to end up doing a random walk if you're not careful. Yeah, so the problem is if you've got a very flat cost landscape, then you're going to have very small gradients. So you're going to need to have very high precision measurements of the gradient, so very high precision measurement of the cost in order to figure out what the cost minimizing direction is. And now this is particularly an issue in the context of trying to minimize a quantum cost, because your cost is going to be obtained statistically by running a quantum circuit many, many times. And so to measure your cost to a high degree of precision is going to require a lot of shots, and so be resource intensive. Or more precisely, 1 over sigma squared shots are required to estimate a cost to precision. So great. Okay, so how do we know if our landscape is nice and textured or flat and untrainable? Well, we can assess the trainability of a variational quantum algorithm by studying its expected cost gradients. So it's pretty straightforward to show for the type of ansatz that I showed at the start, that your average cost gradient is going to vanish. That is, your cost landscape is unbiased. What goes down must come up. But just because your cost landscape is unbiased, that doesn't say anything about its trainability. So both of these cost landscapes are unbiased. The average cost gradient vanishes, but the bottom one is clearly untrainable, but the top one looks like it should be trainable. So to assess the trainability of an ansatz, it's helpful to recall Chebyshev's inequality. So this bounds the probability that the partial derivative of the cost is greater than some delta in terms of the variance in the partial derivative of the cost. So if the variance in the partial derivative of the cost is small, this means that the probability that the variance in the gradient of the cost is greater than the small amount delta is going to be tiny. So small variance entails small cost gradients. Okay, so the first paper to assess the trainability of variational quantum algorithms is this seminal one by Jared McLean. So what they showed is that if U of theta, your parameterized quantum circuit, your ansatz, or at least the ensemble of unitaries accessible by your ansatz, forms a 2 design, so that is, it agrees with the half random distribution up to the second moment, then the variance in the gradient of cost is going to vanish exponentially with the size of the problem. So here, n is just the number of qubits that your unitary acts on, so the number of qubits that your problem is defined for. And then if you combine this with Chebyshev's inequality, it entails that the probability of observing non-zero gradients is going to vanish exponentially with problem size. And well, if you can have exponentially vanishing gradients, you're going to need an exponential number of shots in order to do your training. So for small scale problems, your gradient, your cost landscape might be sufficiently featured to enable training, but for large scale problems, your landscape is going to become overwhelmingly flat. And this is known as the barren plateau phenomenon. Okay, but what I want to point out to you is that this result can be reinterpreted in terms of expressibility. So an ansatz that forms a 2 design is a perfectly expressive ansatz. It's one for which the expressibility measures epsilon rho and epsilon h are going to vanish perfectly. And so this means that perfectly expressive ansatz are going to exhibit barren plateaus and hence be untrainable. Okay, but the converse isn't true. So this was shown in, I guess, first hinted at by this paper by Marco, where what they show is that for a global cost, so that is a cost where your measurement operator acts non-trivially on all qubits, then you can have a barren plateau even with very short depth ansatz. So even a single layer ansatz, which is going to be highly inexpressive, can have a barren plateau if you're dealing with a global cost. So this shows that inexpressive ansatz can be untrainable. Okay, so we have that perfectly expressible ansatz are untrainable, but inexpressive ansatz can be trainable, but can also be untrainable. It's natural to ask whether or not we can formalize this trade-off. Okay, and that's precisely what we do in this paper. So we derive this upper bound on the variance in the gradient of the cost in terms of the expressibility of the ansatz you're using. So on the left-hand side here, we have the variance in the gradient of the cost for an arbitrary ansatz that you're interested in using. Then the first term on the right here is the variant in the gradient of cost for a maximally expressive ansatz. As I argued earlier, this vanishes exponentially with the size of the problem. This was shown by Jared McLean. And then the second two terms. Now, the precise form of these terms don't matter too much, but the core thing to notice is that these are expressibility dependent, such that the higher the expressibility of your ansatz, so that is the smaller epsilon rho and epsilon h, the smaller the upper bound on the variant in the cost partial derivative is. So that is the smaller the variance in the partial derivative is going to have to be. So it means that highly expressive ansatz are going to have flatter cost landscapes and consequently be harder to train. So that draws this fundamental trade-off between the expressibility and the trainability of an ansatz. And also this bound we expect to be more widely useful because prior results only applied to trying to use ansatz that form two designs, but most ansatz you're going to use are not going to actually be two designs, whereas this bound holds for generic ansatz. Okay, so that's our main result, this upper bound linking expressibility and trainability. But a key thing to notice is that it leaves wiggle room. So inexpressive ansatz may, but are not guaranteed to exhibit larger cost gradients. So this prompts a question of when and how can reducing the expressibility of ansatz increase expressibility? Increase trainability. So we decided to explore this numerically. So we considered an ansatz of this form, so alternating layers of fixed gates and random single qubit gates. Fixed gates are just ladders of ZZ, and then the single qubit gates are just we randomly apply an X, Y, or Z gate with some continuous parameter theta. So the first thing we looked at was the effect of the variance in the partial derivative of the cost on the number of layers, so the depth of the ansatz. What we find, as expected from Marco's cost function dependent bound plateaus paper, is that for local costs, reducing the depth of the ansatz substantially increases the observed cost gradients, but for local costs, for global costs, you're screwed either way. You can use a really short depth ansatz and you're still going to have exponentially vanishing cost gradients. Second thing we tried was correlating parameters. So first thing we tried was correlating layers. So that's shown in orange. So that is, we assumed that each qubit could rotate by a different angle, but it rotates by the same angle each time. Then we considered correlating qubits. So all the qubits rotated by the same angle, but it varied from layer to layer. And then we tried correlating everything. Basically, we just had a single rotation angle. And what you can really see is that basically the more you correlate things, both for local and global costs, the higher the observed gradients. And then we also tried restricting rotation directions. So instead of allowing these to be X, Y, or Z rotations, we considered just X or just Y rotations. And in the case of a local cost, this substantially increased cost gradients. Final thing we tried was restricting rotation angles. So in sort of the basic ansatz, we allowed the angles to vary between 0 and 2 pi. But what if we only allowed it to vary between theta tilde and theta tilde plus 2 pi r? So if r is 1, you've still got the full range of rotation angles. But if r is small, you're just exploring a smaller parameter regime. And then we tried two different variants on this. We tried the case where theta tilde was chosen randomly. And then we tried the case where theta tilde was chosen to be close towards the solution. And what we find is that if we have a random initialization, vastly reducing rotation angles range doesn't do much. And the explanation for this is you're then essentially just exploring a small region of the bound plateau. So when you pick randomly, you're likely to be on the bound plateau. And if you just explore a small region of the bound plateau, you're still going to be on the bound plateau. But if we initialize close to solution, restricting the rotation angles has a dramatic effect, particularly for local costs, on the observed cost gradients, because you're essentially just exploring the region around the minima where cost gradients are expected to be larger. Okay, so that's the coming to the end of the first half of my talk. Take-home message is there's a trade-off between expressibility and trainability, and one of them's got to go, and it looks like that's going to be expressibility. And that is because the important thing to note is that your ansatz does not strictly need to be expressible in order to contain a solution. It just needs to be complete with respect to the problem you're actually solving. So what we're going to want to do is try and come up with good problem-inspired ansatz that that are likely to be complete with respect to your particular problem, i.e. something like this for problem A, but not actually explore the total space too fully. And it's easier said than done. It's an interesting challenge, and I think it's a good project for the future. The alternative is we can also try and use perturbative approaches. So the results I showed you on the previous slide showed that things like exploring a smaller region or correlating parameters could substantially increase the observed cost gradients. But of course, your solution may not be one with highly correlated parameters. So you could potentially use those strategies as a sort of pre-training approach. You start off with correlated parameters, and then you sort of perturb away from that by slowly decorrelating your parameters as you get close to the solution. So there are all sorts of strategies that we can explore to try and mitigate this trade-off. However, and this is what I'm going to tell you in the second, hopefully shorter part of the talk, is that some problems are untrainable, no matter how clever your ansatz is. So no matter what clever techniques you come up with, you're not going to be able to solve them using a variational quantum algorithm or quantum machine learning more generally. Actually, before I go on to that, were there any questions on that half? You can also leave it to the end. Cool, I will keep going. So to illustrate the second part of my talk, and just sort of add a bit of color to it, I'm going to start by recalling the Hayden Preschool thought experiment. So in this thought experiment, Alice throws her diary, a secret diary, coded, of course, at a quantum state, as all diaries are, into a black hole that we model, of course, as a unitary system, a scrambling unitary. The question is, can Bob recover it? Well, given that black holes are nature's fastest scrambler and rapidly spread information contained within the initial conditions of a system throughout many degrees of freedom, it would, you would have thought, be pretty unlikely that Bob would be able to do it. But Hayden and Preschool argued that actually if Bob knows the scrambling unitary implemented by the black hole and shares a maximally entangled state with the black hole, then actually just by collecting a few additional photons in the black hole, it'll be possible for him to decode Alice's secret diary. But then natural thing to ask is, well, how the hell would Bob learn that unitary in the first place? And what I'm going to argue is not using a variational quantum algorithm, or actually sort of quantum machine learning methods more generally. Okay, but first things first, let me just go back a few steps and sort of specify what I mean by scrambling. So scrambling, in broad terms, is the rapid spread of entanglement in information throughout many body quantum systems. Pretty essential to understanding black hole physics, but also it's applicable to a whole wide range of areas. So thermalization phenomena, scrambling systems tend to thermalize rapidly. Random quantum circuits, so as I'll come to next, sort of a scrambling unitary can be modeled as a typical random unitary. Particularly highly recommend this paper here, actually, particularly the archive version. In the archive version, they are very pedagogical and include a bit of sense of humor. Even connections between scrambling and fluctuation relations in thermodynamics, as well as a number of other things I don't have space in my slide for. Okay, so scrambling imported a wide range of areas. How do we actually recognize it? Well, it's typically diagnosed using out-of-time order correlators. For example, this one I have here. This is just 1 minus half times the commutator between two local operators squared. So yeah, X and Y are local operators. So for example, they could be local Paulis. X tilde is the time evolved local operator. So time evolved initial local operator. So V here, you could see it as an evolution unitary under some Hamiltonian. You could see it as time dependent. And then this average is taken over an infinite temperature state. Okay, so the OTOC of a scrambled system decays rapidly. So at time 0, this V here is just going to be identity. Your X and Y are local operators, so they commute. So the commutator vanishes and the OTOC is just going to be 1. But if this unitary here is a scrambling unitary, then your scrambling unitary is going to rapidly transform your local operator into a global operator. This global operator will cease to commute with the initial local operator. So the commutator will grow rapidly and the OTOC will decay rapidly. Or more concretely, as recognized by a number of people, but I think sort of argued especially nicely in this paper. The OTOC, the scramble system, rapidly tends to a minimal value that is equivalent to taking its average over a random distribution of unitaries. And that means that we can model a scrambling unitary just as a typical random unitary. Or actually, more precisely, you'll note that this function here only involves 2 copies of V. So one for this x tilde, one for that x tilde. So that is averaging this function over a 2 design is going to be entirely equivalent to averaging this function over a random distribution of unitaries. So that is the OTOC scrambling system rapidly tends to a minimal value is equivalent to taking its average over a distribution of unitaries that agrees with the random distribution up to a second random, i.e. 2 design. And so we don't actually need to model a scrambler as a perfectly random unitary. We can also just model it as a typical pseudo random unitary. So a unitary drawn from a 2 design. Okay, and so now the question I want to ask is, well, can we use a variational quantum algorithm to learn, compile a target scrambling unitary that is a typical pseudo random unitary, typical unitary drawn from a 2 design? Well, how would you go about it? Well, you go about it trying to use a compiling cost of the type that I set out earlier. So just sort of recalling that you can have a cost of this form in order to try and learn a compiling, in order to try and learn a target unitary. This one here was just basically the average fidelity between a state acted on by V and your parameterization. So V is just going to be your target, your typical scrambling unitary. But actually there are more general compiling costs you could use. And we do consider some more general compiling costs in the paper, and I've got a bonus slide on that if you're interested in knowing how we generalize this. Okay, so that's the question we wanted to ask. Can you use a compiling cost to learn a target scrambling unitary? And well, as you might have guessed, the answer is not easily. So we proved that for compiling cost to learn a scrambling unitary, modeled in a unitary drawn from a 2 design, well, the average cost gradient is going to vanish, and the variance in the gradient of cost is going to vanish exponentially in the size of your problem. So this average here is just averaging over an ensemble of scramblers modeled as an ensemble pseudo random unitaries, a 2 design. And sort of sewing these 2 things together by Chebyshev's inequality, what we get is that the probability that the gradient cost is non-zero for a typical scrambler vanishes exponentially with the size of the problem. And crucially, this result holds for any choice in ansatz. So we get this scaling out independently of our choice of our parameterized quantum circuit, U at theta. And so this effectively acts as a no-go theorem for learning scramblers using variational quantum algorithms, quantum machine learning. Because you're not going to be able to do it for large-scale problems because you're going to encounter this barren plateau where training becomes exponentially expensive. Okay. So just to sort of illustrate this a little bit, we ran some numerics. So because we wanted to be able to model approximate scramblers here, we used the model of scramblers from this PRL by Swingle et al. So here, scrambler is modeled as sort of alternating all-to-all entangling gate and random single qubit rotations. And in this paper, they show that this does actually lead to scrambling behavior. So the extent to which this model is scrambling depends on the strength of the entangling gate G and the number of layers applied. So sort of scrambling time T. And on the right here, we plot a cross section through the cross landscape for a highly scrambling unitary. So highly scrambling means large G and large T. And what we find is that the cost landscape is almost entirely flat, with just a narrow gorge where the cost gets down to the minimum. In contrast, for a non-scrambling unitary or very weakly scrambling unitary with small t and small g, the cost landscape is much wider and much more textured, allowing more effective training. So I think that's just a nice visual representation of how the barrenness of the cost landscape depends on the degree to which the target unitary is scrambling. Another way of seeing this is, so here we plot the variance in the partial derivative of the cost as a function of the scrambling time. And what you indeed see is that over time, as your unitary becomes more scrambling, the observed cost gradients decrease. And indeed for a highly scrambling unitary, so for large T, your cost landscape, not your cost landscape, your variance in the partial derivative of your cost vanishes exponentially, as predicted by our analytic results. Okay, so in summary, we find that we've sort of proven that barren plateaus will be exhibited by scramblers, and that is any cost function, local or global, you use to try and learn a scrambling unitary. For any choice in ansatz, you can find that the typical partial derivative for your cost vanishes exponentially with the size of your problem. But we also, so it's important to note that because we model a scrambler as a typical random unitary, so a unitary drawn from a 2 design, our result was also going to hold for the learning of typical random unitaries. So in that sense, randomness is a barrier to trainability. You're not going to be able to learn typical random unitaries. And so in that sense, there are sort of fundamental limits to quantum machine learning. Certain problems, learning typical random unitaries, typical scrambling unitaries, it's not going to work for. That said, sort of luckily, thankfully, I think most physically interesting systems that we might want to try and probe using variational quantum algorithm or quantum machine learning are sufficiently structured that they don't resemble a random unitary. Like, physics would be really hard if we were always trying to learn sort of completely unstructured problems. Normally the problems that we want to tackle do have some structure to them. So in that sense, I don't think this result is in any way condemns quantum machine learning, but rather just tells us we need to pick our target problems carefully. And I think sort of in that vein, further research is required into what systems cannot be learned. And I thought I'd just end by flashing up this slide again. So what have I told you? Well, I've tried to pin down 2 requirements for an algorithm to be variational quantum algorithm to be effective. So the first of these are expressibility, second is trainability. The first result I shared with you is a trade-off between them, showing that you can't have both. The more expressible your ansatz is, the harder it's going to be to train. So we're going to need to come up with sort of problem-inspired ansatzes that aren't highly expressible, and so open up the potential for training. I'm also going to need to pick our target problems carefully, because for some problems, namely learning typical scrambling unitaries or typical random unitaries, no matter how clever your ansatz is, you're not going to be able to train. And I think that's everything I had to say. Does anyone have any questions?
All right. Thanks a lot for a very interesting seminar. Any questions for Zoe?
I had a question, but I'm not really sure how to express it properly. So here goes. So the idea is that the more expressible you make an ansatz, as in more of the space it covers, you're just not going to be trainable. Your gradients are going to be too low. So it doesn't matter that you can reach every point. By randomly initializing it, you can't make it to that point, right? So I don't know if this is going to sound stupid, but if we divide our space initially, for example, into like, if it's a square, if you divide it into quadrants and you create an ansatz for just one quadrant, just as an example, then you can have a less expressible ansatz and make it more trainable and kind of do that 4 times. I mean, just as an example, if you split up your space and do that multiple times, will that help?
Yeah. I mean, that's sort of what's going on here. So by doing things like reducing the number of layers, correlating parameters, or actually even more explicitly, reducing rotation angles, you're going to be just exploring a small region. And I guess the thing is, so say you explore a small region and you're just in completely the wrong region, you're just going to get stuck. So you could potentially divide this up into 20 regions and just try one region at a time. And then naively, when you're on these middle 2 regions, yes, you will be able to train, and when you're on the other regions, you're not going to be able to train. I think just randomly splitting up your space and trying and training on different regions at different points in time is not going to be the most clever strategy. Ideally, what you want to try and do is come up with a good starting guess. And that's going to be trying to use the physics of the problem. So you're going to be using the symmetries to realize actually you can correlate certain parameters, that you're not interested in particular regimes of very high entanglement or very low entanglement, things along those lines. So I think you've got the right kind of idea, but you just want to do it a bit more cleverly.
Okay. That makes sense. Okay. Thanks.
So I have a question about learning scramblers at the end. But yeah, so your result precludes learning scramblers by VQAs, but it leaves open the possibility that you might be able to learn them by other methods. Is that a possibility? Or like you also said using quantum machine learning, but from what I understood, your analysis applies to this model of having ansatz that consist of layers, like constant layers and rotation gates on single qubits.
Okay, so this is a question that me and my co-authors have discussed many times, and we've tried to figure out what is fair to say here. So firstly, I think I can't think of a method for learning a unitary on a quantum computer. So compiling a unitary on a quantum computer, I can't think of a quantum machine learning method for compiling a unitary on a quantum computer that doesn't look like a variational quantum algorithm. So you could say, oh, what about like kernel methods? I don't think they could be used here. Therefore, sort of characterization problems, not for trying to compile a unitary. You could say, are the class of ansatzer we consider broad enough? Are the class of cost functions we consider broad enough? So we consider more general compiling cost and ansatzer than the ones I showed back before. So we also consider cost of this form, where our ansatz can be a channel. And we basically allow for we also allow for entangled training data effectively, because we're going to have our target act on only part of our input state and part of what ends up getting measured. So this makes things more general. I mean, yes, there will be some cost functions you could consider potentially to compile a cost that do not take this form. Like a really naive one would be, what if you just, I was going to say square it or take the log of it, something along those lines. You could potentially do something like that, and it wouldn't fit into this framework automatically. But it wouldn't fit into this framework automatically, you just squared it or took a log of it. But I suspect that it would be pretty straightforward. If you gave me a generalization and said, try and generalize your proof to this case, I suspect it would generalize. It's just a question of how painful it would be to do that generalization.
Yeah, in fact,
Oh, sorry.
Sorry.
I was going to ask another related to that question. So a different model for a unitary, and I don't know if this makes sense, but it would be like, every operator you can write as a linear combination of Paulis, right? And suppose that your unitary were a linear combination of Pauli strings, and there's not a lot of Pauli strings. And I don't think your result would preclude. So you could try to learn the unitary by doing Pauli measurements and trying to learn the coefficients, right?
So that would be a sort of process tomography type thing. I think process tomography is just not scalable, is the problem.
No, but what I'm saying is, suppose that the unitary you're trying to, I guess you're looking at scramblers, and I don't know if they would fit into this, but suppose that the unitary that you're trying to learn can be written as a linear combination of a number of Pauli strings that's linear in the number of qubits. And then the objective would be to learn the coefficients, right? So, I guess the point is that your result would not apply there, right?
So you are essentially advocating a process tomography type approach.
No, I'm saying the unitary can be written like that.
But then how are you, so you're not implementing it on a quantum computer?
Well, that's a good question. I mean,
so it wouldn't, what you're suggesting wouldn't fall into this framework. So this task of trying to find U of theta opt, so that's U of theta opt equals V.
Yeah.
It sounds to me like process tomography, but maybe I'm not fully understanding.
Yeah, maybe I'll change it slightly where what I'm describing is the Hamiltonian. And
Yeah.
you would do, Hamiltonian simulation to implement the unitary.
There are interesting questions there. So Hamiltonian learning is a whole nother sort of big field in quantum machine learning. And it would be nice to prove that scrambling Hamiltonians cannot be learned using quantum machine learning. That would be a whole different framework.
Okay.
It's something we've discussed, and I can't remember why we've not gone into it. But yeah, you could think about the problem in that context.
Okay. Thank you.
Yeah. May I ask?
Yeah.
Since you have the slide in front, I was going to ask, now it is indeed, when you say variational, what is variational here is the C of theta, the classical, the optimized, that's what you have minimized. So this is not variational for either the U or the psi of theta of the quantum computation side. So it is indeed true that what you're doing variational is really on the right-hand side, on the classical computation, on the C of theta. Am I right?
So the classical computer will just tell the quantum computer, it will give it, I want you to do theta primed. I want you to run you with respect to the set of parameters theta primed.
Right.
And that costs, the quantum computer just runs that circuit.
Right. But my point is that the theta that you're doing it for is optimum for the C of theta. It's not necessarily optimum for U of theta or psi of theta. I think
I'm not following that, I don't think.
You see, when you say something is variational, doesn't it mean that if there are sort of first order errors, so to say, in some guess, then the variational thing takes care of the fact of giving only second order errors. That's why it's variationally more accurate. And to me, that is going on for the C of theta, which is indeed the one which is quadratic, the way you set it up with the U occurring twice. Whereas it's not going to variationally give an accurate U itself.
Let me just go back right to the start.
Right, in the very first setup. Yes, this slide.
Even okay, yeah, or here.
C of theta involves U twice. And indeed, so what you have done is you've minimized, or you've got a variationally accurate C of theta. But I'm saying that neither theta nor U of theta need be variationally accurate.
Let me go back even further. Oh wait, that's too far back. Okay, so here, what you do is the classical computer tells the quantum computer what parameters to run this circuit with respect to. And that prepares some state to psi of theta.
Right.
And then that psi of theta is measured.
Right.
And that psi of theta will give cost of theta. And then the classical computer just says it runs gradient descent or whatever your favorite optimization technique is, and tells the quantum computer what parameters to try next. And then the quantum computer tries a different set of parameters. So instead of theta of t, it goes to theta of t plus 1. So the theta is the same for the u, the psi, and the cost.
Yes, but I'm saying that your choice of C of theta, you can make all kinds of choices of C of theta, right? And each one of them will give you a different result for the thetas and the U of thetas and the psi of theta. For instance, if I built a C of theta, which is not quadratic in U, say it's linear in U.
That would be hard to do here in the, okay, so
but that's also a possibility. It depends on how I define my C. Suppose I instead of using U twice, I could use it 4 times. These are all options that it seems to me I can explore. And each one is not going to give me the same result for the thetas and for what is going on the quantum side, the quantum computation.
Okay, so trying to use just U, I mean, you're effectively you're using U once here, because you've just got a U dagger here. I mean, that's just.
Right. But it is U repeated, because basically psi is repeated twice, as you see there in the next line. So this is the usual thing of getting the energy of the ground state. Let's say that the psi of theta would be the ground state wave function. So you could get a very good estimate of the ground state energy but that doesn't necessarily mean that that particular psi is all that good as a wave function. This is well known. For instance, if you take a physical system like an atom, then most of the energy comes from small distances. So it could be that your psi of theta has done a good job of describing the small distance behavior, so it has given you a good energy. But if you are now interested in something about the extremities of the atom, the wave function at very large distances, it might be quite poor for that, because it doesn't contribute that much to the energy or to your C of theta in your language. So that's the point I'm driving at, is that you can indeed tailor your C of theta to different ways, including whether it's linear in U or quadratic in U or in psi, the same language. And so this is what I'm trying to say.
So essentially what you're saying is that you could equally just square this.
Right.
You could, at post-processing, do the cost function squared,
Right.
and that's still going to be
Or maybe a square root.
And you're going to end up with potentially, you'll end up with
a different U of theta, it seemed to me.
I mean, once you get the cost small enough, once you get it all the way down to 0, it's still going to be faithful. So the one that perfectly minimizes the cost is still going to be the same. But yes,
there is only one minimum. Even that, you know, you could get trapped in some minimum which isn't quite the minimum that you want.
Yeah.
I mean, there are all kinds of complications that I can think of.
No, I agree that the cost landscape is going to be different. And
okay, thanks. Yeah, that's just what I was driving at. Thanks.
You know what? That's actually something I didn't address. So when I was sort of on, when I'm on this slide saying, okay, the first thing you do is pick your cost function such that it's faithful. I mean, that's not the only thing to do. So one, you want your cost function to be local rather than global for the reasons I pointed out later on. If it's global, you have a really flat cost landscape. You also ideally don't want too many local minima and things along those lines. You want to have, there's so many other features that you can think about, but they're often so hard to address. You don't even, it's very hard to tell what your cost landscape is going to be like when you first come up with the cost function. But in the ideal world, yeah, you take all of those things into account.
Thanks.
All right. I guess there are no other questions. So thank you for the seminar, Zoe. It's very nice. I'm going to stop the recording now.